In the last unit, we looked at a quantity called the stagnation enthalpy. This is the enthalpy that a flow achieves when you bring it to rest without adding or subtracting any heat. However, most of us don't have much of an intuitive feel about what a stagnation enthalpy of, say, 4 megajoules per kilogram means. So in this unit, we're going to look at the stagnation temperature because most of us have a good feeling for what different temperature levels mean and what the consequences of having these temperatures might be. To derive an expression for the stagnation temperature T0, we begin with our expression for the stagnation enthalpy H0, which is equal to the enthalpy H plus a half the velocity squared. For a calorically perfect gas, the change in enthalpy between two states is equal to the specific heat Cp multiplied by the temperature difference between those two states. So let's apply this between the current state of the gas and the stagnation state, which is denoted with that subscript 0. The difference between the stagnation enthalpy and the static enthalpy H, where that static term just means the current enthalpy of the fluid, is going to be equal to Cp times T0 minus T. And from our expression for stagnation enthalpy, this whole thing has to be equal to a half the velocity squared. So if we divide through by Cp and rearrange, we find that the stagnation temperature T0 is equal to the current temperature of the flow T plus a half the velocity squared divided by Cp. There are two important limits to this relation. If the velocity goes to 0, then we're converting all of the kinetic energy of the gas into thermal energy. So the temperature tends to that stagnation temperature T0, which is the maximum temperature that the flow can achieve without adding any extra energy. The other important limit is a bit more theoretical. If the temperature tends to 0, then we're converting all the thermal energy into kinetic energy, and the flow speed reaches a maximum value of the square root of 2Cp times T0. Now this is a much more theoretical limit. It's very difficult to achieve in practice. But if you were taking this course, let's say from a module of the International Space Station, and the airlock suddenly opened and the air rushed out into the vacuum of space, which is at near absolute 0, and somehow that gas didn't freeze as it was escaping, it might approach a speed close to Vmax. Next, let's express T0 in terms of that fundamental quantity which is most important for characterizing a compressible flow, the Mach number. We can do this by first dividing through our expression for the stagnation temperature by the static temperature T. Next, let's multiply and divide the last term by gamma R, so on both the numerator and the denominator. Then what we can see is that we have a gamma RT on the denominator, which is equal to the sound speed squared. If we combine that with the velocity squared on the numerator, we now have a factor of the Mach number squared. We've got this remaining factor out the front of gamma R on Cp, and we can simplify that a little bit using the fact that the gas constant R is equal to Cp minus Cv, and the ratio of specific heats gamma is equal to Cp divided by Cv. So if we combine these two, we find that gamma R on Cp is just equal to gamma minus 1. Combining this with the bit of manipulation we did above, we find that the ratio of the stagnation temperature of the flow T0 to its current temperature at Mach number Mt is equal to 1 plus gamma minus 1 over 2 times the Mach number squared. So this relationship tells us some very interesting information almost immediately. It tells us, for example, why when we put our hand out the window of the car as we're driving, the palm of our hand doesn't begin to get hot. This is because our car is probably moving at a maximum Mach number of about 0.1, and 0.1 squared is very small. And gamma minus 1 over 2 for air is only 0.2. So this means that the stagnation temperature against the palm of our hand as we're driving in our car is only a tiny fraction higher than the ambient temperature of the air. In one of the problems that follow this video in the unit, you'll actually calculate just exactly what this fraction is. So that example with the car was a very low Mach number flow. What about if we're going a bit faster? what are the consequences for the stagnation temperature? We're going to look at some aircraft flying at different Mach numbers, all at an altitude of 12 kilometers where the temperature is 217 Kelvin, which is well below the freezing point of water, and for air, gamma is equal to 1.4. So what we're going to do is calculate the temperature against the stagnation point of these vehicles where the flow is brought to rest. The first example is of a Boeing 747-400, which has a cruise Mach number of about 0.85. If we apply our relation for stagnation temperature to these parameters, we find that the stagnation temperature is about 249 Kelvin, which is still well below the freezing point of water, 273 Kelvin. So if you could put your hand out of the window of a 747, which I wouldn't advise, then in addition to having a severe shortage of oxygen, you'd also probably get a severe case of frostbite. What about if we ramp up the Mach number even further to a supersonic aircraft? So let's look at the Concorde, which has a flight Mach number of 2. If we calculate the stagnation temperature, we find that it's now jumped up to 391 Kelvin. This is above boiling point, which is 373 Kelvin. So if you put your hand out the window of the Concorde, again, not advising this, and also it's out of service unfortunately, you would get a severe scald as that airflow stagnates against the palm of your hand. So looking at an even higher Mach number aircraft, the SR-71 Blackbird, which has a flight Mach number of 3.2, the stagnation temperature is now 661 Kelvin. That's pretty high, hundreds of degrees above boiling point, but it's still well below the melting point of most common metals used in the aerospace industry. But if we go to a hypersonic vehicle, then things become much more severe. This is the HiShot 2 flight experiment. It was the first flight experiment to demonstrate supersonic combustion in flight, and it had a flight Mach number of 7.6. The stagnation temperature against the leading edges of this vehicle was 2,724 Kelvin. The melting point of even high temperature steel alloys is only 1,800 Kelvin. So to get this vehicle to survive for more than a few seconds is a massive challenge. The design of this vehicle used a copper alloy for the body, which soaked up the heat during the test time. But if you wanted to design a scramjet that survives for a long period of time, you have to find other and more complex ways of overcoming these massive thermal loads. Things become even more severe at higher Mach numbers. In one of the problems for this unit, you're going to look at the stagnation temperature against the leading edges of an access to space scramjet, which is flying at a Mach number of up to 12.